Okay, so at this point we've figured out a couple of nice things about how electromagnetic waves work in vacuum. We've looked at plane waves, and we've looked at spherical waves, which are sort of your most fundamental geometries. And now we're going to expand things to include the possibility of matter. Not everything takes place in a vacuum. The way we're going to transition over into that is we're going to start with a wave in vacuum and see what happens when it crosses an interface into some dielectric, some nice planar interface or boundary. Now, for the most part, that's not really going to change anything, except for the replacements of epsilon naught with epsilon and mu naught with mu. And to make things easier, in non-conducting materials, mu is so close to mu naught as to make that change basically negligible. So all we really have to do is replace epsilon naught with epsilon. Pretty small change, but it has some rather significant consequences. The most fundamental of these is the fact that the wave speed is going to change. So c is given by 1 over root epsilon naught mu naught, and the wave speed inside material is going to be given by 1 over root epsilon mu. So inside a material, the speed of light is different than it is in vacuum, and it is always lower than it is in vacuum because epsilon and mu are always greater than epsilon naught and mu naught. So what we're going to do is we're going to define the index of refraction as the ratio of c to v for some material. And of course, that index of refraction will always be greater than or equal to 1. As it turns out, we can use that one fact plus the Maxwell equations to derive some very fundamental rules of geometric optics. Here's what we're going to do. Let's suppose we have some planar interface. In this picture, it's going to be the YZ plane. And let's suppose we have plane waves coming in along the x-axis, making some arbitrary angle and hitting that interface. So there are 3 waves being indicated in this picture. The first one, the incident wave, is the K wave, and it's going to make some arbitrary angle theta with respect to the normal to that interface. And then we're going to allow for the possibility that there's some wave coming out the other side of that interface. We'll call that the prime wave with some wave vector K prime and some theta prime. We'll call that the transmitted wave. And furthermore, we'll allow for the possibility that there's another wave coming back to the left from that interface. We'll call that the double prime wave with some angle theta double prime and some wave vector K double prime. That's the reflected wave. What we're doing right now is we're trying to set up this problem with as few constraints as possible. We don't really know what's going to happen. We don't know what the thetas are going to be relative to one another. We don't know what the wavelengths and frequencies are going to be relative to one another. We're just going to say, all right, there's one thing we know. There's an incident wave coming in from the left. And there might be these other waves going off to the right or to the left as a result. And we're going to take what we know about Maxwell's equations to pin all these variables down. And to keep things clean, we're just going to look at the E fields involved. It's easier to get the B fields from those. So, this is a boundary value problem. We have fields on the left and fields on the right. The sum of all the fields to the left of the interface are right here. Note that I'm being very diligent about putting double primes on everything, on the amplitude, on the wave vector, on the frequency, all of that, because we don't really know anything at all about that reflected wave. And let me remind you that that K vector is the wave vector. The wave vector tells you 2 things. 1, it points in the direction of propagation, and 2, its magnitude is 2 pi over the wavelength of your wave. Okay, and on the right-hand side of that interface, we have a field composed of just 1 wave. With those fields down, all we need to do is use boundary conditions to stitch them all together. So we have 4 good boundary conditions for the parallel and perpendicular components of various fields. There's no free charge, which means that del dot D is 0, which means that the perpendicular component of D is continuous. Del dot B is 0, which means that the perpendicular component of the B field is continuous. We know that the parallel components of E are always continuous. And since there are no free currents anywhere, the parallel components of H are continuous, which we can, of course, write as a condition on B. So the whole problem becomes simply taking those two fields, the fields on the left and the fields on the right, and stitching them together with those four boundary conditions, or whatever subset of them we need. Okay, for my first trick, I'm going to point out that these exponentials, which involve k and t, can be written as something split out like this. And we have equalities where we have something like, all right, these fields over here with exponentials equal these fields over there with these same kinds of exponentials, but different k's and different omegas. So you have to be able to look anywhere on that boundary, vary x or t independently, and have the various equalities that come from those boundary conditions hold. And the only way you're ever going to get that to work is if all of these omegas in this term are the same. If these things are varying in unequal ways, you're never going to get those equalities to hold for all time. And so right off the bat, we see that frequency cannot change when an electromagnetic wave crosses an interface. But we know wave speed changes, and we know v equals lambda f. So that implies that the wavelength will change. Continuing on in this fashion, I'm going to go ahead and make a very useful representation of the magnitude of the wave vector in terms of omega, which is constant, c, which is constant, and the index of refraction. So now we can see very transparently what happens to that wave vector, and thus the wavelength, when n changes. Now let's look at the material on the left. Over there, we know omega and omega double prime are the same. And we know n and n double prime are the same because they're the same material. So considering this little fellow right here, it must be the case that the magnitudes of k and k double prime are the same. Contrariwise, it's not going to be the case that k equals k prime. The wavelength of the transmitted wave will definitely not be the same as the incident or reflected waves. Instead, what we're going to do over there is say, well, omega is still omega prime, which means k times v equals k prime times v prime, which gives us a way to solve for k prime in terms of k, or vice versa, by involving the indices of refraction. Alright, next let's take a look at that e to the I k dot x term. Remember that stuff I was saying about needing to be able to vary different variables independently without breaking the equality? Same thing's going to happen here. The boundary conditions and the equalities we get from them are going to have to hold everywhere in the yz plane. So we have to be able to vary y and vary z independently any way we want without breaking this equality. And the only way we're going to be able to do that with terms like this in here is if every term has the same k sub y, and every term has the same k sub z. Now the direction normal to the interface, the x direction, well, we can't say the same thing there. But we have discovered a number of useful constraints. We can make all the omegas the same, all the k sub y's the same, all the k sub z's the same, and that's going to make this a lot easier. Now that interface is the yz plane, and without loss of generality, we can just drop the z, ignore it, set kz equal to kz prime equal to kz double prime equal to 0, and just worry about the x direction and the y direction, and that contains all the pertinent information. So let's do a little bit of geometry involving those vectors and those angles theta. The magnitude of the k vector is n times omega over c. And if you work out the geometry with your sines and cosines to find the components of those k vectors, you get a little something like this. Keep in mind that the magnitudes of these two k vectors have to be the same. And also, the y components of those vectors have to be the same. So here's the y components. So it looks like sine theta has to be equal to sine theta double prime, which means that theta equals theta double prime, which is the law of reflection, which was hiding in electromagnetism all along. One thing I'd like to make extra sure you're noticing is that we are measuring theta with respect to the normal to the interface, not with respect to the interface. Let's see if we can't get theta prime and k prime involved in this. We remember on the last page we came up with a relationship between the magnitudes of the two. And we can use geometry to write out the k vector in terms of this time the index of refraction of material 2 and angle theta prime. We will once again exploit the fact that the y components of all of the wave vectors have to be the same, and compare k to k prime. And we're going to discover that the y component of k has to equal the y component of k prime, which gives us n1 sine theta 1 equals n2 sine theta 2, or Snell's law of refraction. So to recap the major results today, when you have a wave passing through some interface, frequency doesn't change, wavelength and wave speed do change, the law of reflection holds, and Snell's law holds. That's pretty good progress right there, so why don't we knock off? And next time we're going to look at something called an evanescent wave, which should call to mind some ideas from quantum mechanics yet again. I'll see you there.